rising senior at the University of Maryland, and today I'll be presenting automatic energy analysis using types. So, embedded systems are increasingly prevalent and are deployed to a diverse range of applications, ranging from your personal device, such as a smartwatch, to medium-scale applications, such as smart agriculture, to the remote extents of outer space. Now, in order for embedded systems to communicate with the outside world, they make extensive usage of peripherals, such as a gyroscope or a Bluetooth sensor in a smartwatch. Because these systems are deployed to a diverse range of applications, there is an urgent need to understand the energy requirements of these systems and develop energy-efficient applications. For example, it would be really annoying to have to constantly recharge your smartwatch every hour or so. In medium-scale applications such as smart agriculture, it can be very financially expensive to have to go into the field and replace batteries. And in the depths of outer space, it can be literally impossible to replace a battery once it has died. However, peripherals make understanding the energy requirements of these systems much more difficult, as peripherals typically have complex state, as can be seen here, which makes it hard to understand how exactly they interact with the rest of the system. So prior work to understanding these energy requirements typically falls into two major categories, either measurement-based approaches, which literally measure the amount of energy an application consumes while running, and this is extremely accurate. However, it can be very difficult to incorporate into an existing workflow and actually perform for an average developer. On the flip side, there's also many static analysis approaches, which is very easy from a programmer's perspective, as it simply operates as a compiler plugin and typically needs little to no input from the programmer. However, as a static analysis, it may not be able to capture all of the fine-grained peripheral interactions and state that is present. So the question is, can we have a tool that does both, captures fine-grained peripheral interactions while also being accurate and easy to use? So our answer to this question is yes. And today I'll present a type system called Heliod, which is able to do just this. It combines both type state and automatic amortized resource analysis to have precise peripheral state tracking and enable robust cost bounds. Importantly, we report these costs symbolically in order to aid programmer understanding. So how does our tool work? Well, in order to be able to accurately report the cost of using these peripherals in an embedded system, we have three main categories to consider. The first, of course, is executing instructions on the main board. The second is any operations that a peripheral performs. But finally, most importantly, we also have to consider any peripherals that are active in the background. Let's look at a simple example. Here we have a code snippet of using an I2C bus to perform a simple task. We first start by transitioning the I2C bus into TX state. Then we initiate the transmit operation. While this transmit operation is going on, we importantly perform some computation on the main board, represented by some other func. Importantly, while this function is executing, we also have to consider the fact that the I2C bus is in the TX state and performing some operations. Finally, once the transmit has completed, we call the stop function in order to transition from the TX state to the stop state. And most importantly, by utilizing type state, we can have a precise understanding and tracking of the peripheral state throughout the course of execution. So, to correspond with the three categories of cost mentioned earlier, we also have three different types of cost expressions, which represent either cost of executing code on the main board or the cost associated with using a peripheral, such as either being in a state or transitioning from one state to another. Let's look at how this type system works on a larger example. Here we have this function called log data, which takes in a temperature sensor. It then performs a measurement and conditionally writes to a variable depending on the value of this measurement. Finally, it transitions the temperature sensor to a low power state and returns the result of the variable that was written. For each statement that we successfully type check, we also synthesize a cost expression, which represents not only the cost of executing that statement, but also the cost of any background peripherals that are active during that statement's execution. Some costs here were elided for ease of readability. But notably, you might notice, we have no insight on the initial state of the temperature sensor at the start of this function. And this is important because we want to support calling such a function in multiple different contexts. So let's look at some examples. So we have two examples here. And in the first example, we start out by just simply turning on the temperature sensor by transitioning to the idle state, and then immediately call log data. Here, we only have one additional transition to keep track of, and so we can tell immediately that at the start of this function, the sensor is in the idle state. But in this more complex example, what we have is we actually transition all the way to the measure state and perform a measurement. And a programmer might do this because they want to perform some other calculations or some comparisons. And here, we notice that the initial state of the temperature sensor is actually the measure state because of these additional computations. And we have additional costs to consider, including 2 additional transitions and an additional peripheral operation. And importantly, both of these examples are valid. And we want to be able to support expressive and practical peripheral usage. And importantly, the usage of these peripherals determines both the cost of the application as well as the precise peripheral state. So this motivates the need for state inference in order to have a precise understanding of the peripheral state. So how exactly does state inference work? Well, the key insight is that while the internal state can be very complex, it's actually highly structured, very similar to a state machine. So what we notice is that every transition actually gives us a lot of information about the peripheral state. We create a new state variable per transition, which is very similar to a type variable. And we collect constraints based on our knowledge of the internal state of a peripheral. We collect these constraints both when analyzing function body and at the call site. Finally, whenever a function is called, we combine all of the relevant constraints together and solve to understand what the precise set of states a peripheral can be in. And importantly, we store all of these state variables in a stack in order to understand how the—
Sai, 5-second warning.
Thank you. So for some next steps, we want to also support asynchronous peripherals, which are commonly used in many low-power applications, and this requires a generalization of type state. Additionally, we are working on a concrete implementation using Rust and evaluating the effectiveness of our approach. So to conclude, we want—
Sorry, for the sake of time, I'm going to cut you off there just out of fairness, and we will move to questions. Questions from the judges. Oh yeah, applause first. Thank you. Yeah, sorry, just for the sake of time, that was about 15 seconds over, so we're going to go to questions for the judges. Will he be able to hear us? Great, we're going to repeat some questions, so keep them short, judges.
Where does time enter into the equation, like time idling and so forth? I didn't really see that in the system.
So the question is, where does the time enter into the equation?
Many low-power embedded systems, we can actually assume deterministic timing for each of these instructions, and the system can track the timing information for each statement. And then, of course, for function calls, a function is a collection of statements, and so each function call also has associated with it a timing summary, which represents the time that each statement in its function executes.
Thanks.
And we incorporate this with our costs that we report.
Okay, thank you.
Thanks for a nice talk. You mentioned that at the end of the analysis, there's a kind of solving step. Is that fully decidable? Does it have any limitations depending on what kind of patterns you see in the code?
Okay, the question is the solving step that you have shown towards the end of your presentation. Is it decidable, or what are the constraints associated with it?
It is decidable because a peripheral state is modeled as a state machine, and we can represent the state machine as a simple lattice. And because we have these transition statements that the programmer specifies, which tells us at various points in time the concrete state of a peripheral, then we can utilize this along with the a provided state machine description in order to solve for any unknown states that we have.
Thank you. One more question.
Have you considered generalizing, supporting higher order functions and sort of, being parametric over I guess, the state.
So the question is, have you considered higher order functions or parameterizing over state?
Higher order functions, but this is something we want to. And for parameterizing over state, that's definitely something similar to what our approach does, and it's something we support with in terms of function calls and aim to support in general.
Thank you.
Questions from anyone, even if you're not a judge?
Nice talk. May I have a quick question? You mentioned lots of about just the states, and all the thing looks like a state machine, but why you use types?
Could you repeat that question?
Just say that again?
Could you repeat that question?
Oh, so you say all the thing are state, and all the thing likes a state machine. Why you use a type system here?
Okay, given that you're trying to enforce, Sai, the question is, given that you're trying to enforce constraints on a state machine, why did you choose type system to do that?
Yeah, that's a great question. So doing this in the type system provides a couple different advantages. The first and foremost advantage is that a lot of the work on automatic resource analysis is actually related to associating cost with a given type. And so this allows us to, so by encoding the state machine in the type system, this allows us to leverage that prior work and combine with that. Additionally, by encoding this state in the type system, we are actually able to develop this inference algorithm, which means that programmers do not actually have to provide much detail beyond just a state machine description. And finally, by the type system allows for very compositional tracking of the state and allows us to enable, computations with very little limitations. Much of the prior work that was a static analysis typically requires some sort of limitation on how the code is structured in order to make it feasible for the analysis to actually fully execute, which our type system sort of avoids.
Great, thank you. That is all the time for questions, so let's thank our speaker again.